All right, for our final speaker of the day, we're very lucky to have Jeffery Pennington from Google Brain X Stanford, and contributions to machine learning theory, and will tell us about deep learning, free probability training, and generalization. So, take it away.
Yep, thank you. Yeah, it's great to have the opportunity to tell you about some work that I've been doing. It's really hot off the press, and this is still unpublished. This is the first time I'm talking about it, so please bear with me as I try to maybe work out some of the kinks in the storytelling here. But I should also mention that this is work in collaboration with the excellent Google AI resident, Ben Adlam. And so what is on the menu today? After maybe a quick appetizer, setting the stage here, I'm going to serve linearization in 3 ways. Maybe with a palette cleanser of free probability and operator value free probability. I hope that this meal kind of whets your appetite to learn a bit more about these topics, and hopefully I can convince you that these tools are really useful for trying to understand generalization in kernel systems. Okay, so as a way of motivating the discussion here, I'd like to just say a little bit about why I think it's interesting to study high-dimensional models. So first of all, I think one of the main motivations is just, in practice, the deep learning data sets that people typically train models on are high-dimensional in the sense that the number of features is large and the data set is large. And crucially, that the data set is not many orders of magnitude larger than the number of features in many cases. So for CIFAR10 and ImageNet, the ratio is 1/10, 1/100th. We're definitely, for these cases, not in the classical regime where one can take the data set size to infinity. But maybe sort of more theoretically here, I think that the dimensionality of the feature representations for image data sets is just something we've decided as a community as something that's practically feasible to manipulate on, frankly, at this point, old hardware. Whereas the raw physical data that underlies the data set construction process is oftentimes intrinsically high dimensional. So for video or speech data, for example, the features available for solving the problem are many orders of magnitude larger than the size of the features that one actually we have used up till now. So the point here is just that data sets are high dimensional. And of course, we all know that models are high dimensional. And I'd like to argue here that it's worth considering 2 ways, at least 2 ways, in which deep learning models might be large. The first way is if the number of parameters p is roughly on the same order as the number of samples m. And I think another interesting regime is when the hidden layer widths n of your, in this case, fully connected feed-forward networks are very wide, and that they might be on the order of the data set size themselves, which means that the total number of parameters is quadratic in the data set size. So I'd like to come back to this point later, but just to mention that deep learning models are huge with a large number of parameters, whether they're linear or quadratically over-parameterized. If you just look at a couple cases in point here, a fully connected network on CIFAR10 has a number of samples that's on the order of somewhere in between the width of a typical fully connected model and the total number of parameters in that model. And likewise for a ResNet or ImageNet, the number of samples that we train on is also sort of somewhere in between. Maybe it's closer to p than to the width in that case. But generally speaking, these numbers are huge. And I think this motivates considering statistics in high dimensions. So that's going to be the context of the talk. In particular, I'm going to be talking about the asymptotic limits, where all of these parameters go to infinity, namely the data set size, the input dimensionality, and I'll be focusing on single layer cases, so the single hidden layer width n1 are all going to go to infinity at the same rate. There can be some finite constants, phi and psi, that dictate the sort of rectangularity factors or the aspect ratios. So this is the setup. I'm going to neglect to mention throughout this talk any discussion of limits, basically, but keep in mind, under the hood, I'm implying that we're taking this joint limit with these ratios held constant. So this is what I mean by high-dimensional regime.
But you're just considering the quadratic regime.
In this case, I'm going to come back to the linear regime briefly at the end, but yes. So for networks where all of the parameters are trainable, this would be the quadratic regime. For networks where you only train the top layer, for example, where you look at random feature methods, this would be the linearly overparameterized regime. So just as a simple warm-up here to show you how things can be interesting in the high-dimensional regime, if you haven't thought about this before, let's consider, for example, a data set X with entries with features that are all just IID Gaussian random variables. So the data set matrix X is in R n0 by m. And if n0 is held constant, so in the classical regime where you might take the number of samples to infinity, this data covariance becomes trivial, it's just the identity. In the high-dimensional regime, more interesting phenomena can show up. So in particular, if you hold this ratio fixed, like we'll be doing in this talk, the spectrum of the data covariance approaches some non-trivial limiting distribution known as the Marchenko-Pasteur distribution. So you get this one-parameter family of distributions that really captures in some of the non-trivial behavior in the high-dimensional regime. Okay, so this is why I think studying high-dimensional statistics is potentially interesting. Let me walk through how things unfold in probably the simplest possible scenario you can imagine, which is just linear regression. And we're going to do linear regression in a very simple setting where the data points are IID Gaussian, and also the labels are IID Gaussian, independent of one another. This is a super trivial setting. You can think of this as just a pure memorization task. But I just want to highlight some of the methods in this setup before we relax these conditions a little later. Okay, so the loss is just a square loss with a ridge regularization term. And the optimal weights, W star, solving this problem, are given in terms of the resolvent matrix of the data covariance, Q. And if you just plug Q into the loss, you plug W star into the loss and ask what the training area is at the optimum, what you can do is just expand out the terms, and you have essentially 3 terms. Using the fact that Y is IID Gaussian, you can get rid of the Y transpose Y terms in this asymptotic limit. And furthermore, using the relation between X transpose X and the resolvent matrix Q, you can further simplify the expression and basically write down the training error as a derivative of the trace of the resolvent matrix Q. So I'm not saying anything new here. This is just super basic algebra. But the point is the following. The trace of the resolvent is a kind of special object in many ways in random matrix theory contexts. It's known as the Cauchy transform. And given that we know the analytic form for the data covariance spectrum, the Marchenko-Pasteur distribution, you can just write down an explicit expression for the trace of the resolvent. Explicit expression for this Cauchy transform is just the root of a quadratic equation. So this means that you can take the derivative and write down a explicit expression for the training error. As a side note, I just mentioned that the Cauchy transform is a nice analytic object, and if you know it, you can recover the spectral density rho by taking this limit. And if you know rho, you can obtain G. So these things you can exchange between one another. And I'm going to be coming back to this Cauchy transform later many times. But in this context of ridge regularized linear regression with random targets, you can write down an explicit closed form expression for the training loss. I'm not claiming this expression in itself is very interesting. I'm just highlighting some technique here. But OK, here's a plot of some of the result for different values of this rectangularity constant phi that tells you basically how many samples you have relative to the dimensionality of the features. And if you have fewer samples than features, namely phi is greater than 1 or equal to, then for small values of the regularization parameter gamma, you get 0 training loss. And this is just expected because you just have enough parameters to exactly fit the constraints. On the other hand, if you have fewer features and 0, so phi is less than 1, then the asymptotic training error is non-zero. So this is totally trivial. I'm just highlighting what you can do in this high-dimensional regime in a succession of simple cases, getting increasingly more sophisticated. So we talked about that asymptotic training loss. You can also talk about the time dependence of the training loss under gradient descent. So for this, you just basically do exactly the same thing. You know, because this is just a linear differential equation that governs the evolution of the weights, you can write down the time-dependent value of the weights. And it's given by a very similar expression, but now this, what I could call a time-modified resolvent, Q, depends on the time of gradient descent trajectory. So if you take t to infinity with a small enough learning rate in this expression, you get what we had on the previous slide. But you can just do all the same manipulations now that you did previously, expanding out the trace terms and collecting things, and you get a time-dependent expression for the training error. So again, this is just basic linear algebra. Nothing fancy is going on here. But what can you do with this kind of trace object, which contains inverses of the data covariance matrix K? Well, you can use Cauchy's integral formula, which specifies that if you take some matrix function, some function of a matrix argument, then you can evaluate that function by instead performing a contour integral, where you evaluate the function at a scalar argument z, and you take z to go a contour that encircles the eigenvalues of A. So this is just a standard identity in complex analysis. But it allows us to do some nice stuff. For example, if you just take the trace of that equation and substitute our formula for f of k, then we get an explicit expression for the time-dependent training loss in this ridge regularized regression problem with random targets. So again, G is just this Cauchy transform. We evaluated a complex argument that depends on the regularization constant gamma. You do this contour integral, and you can get the exact training curves for linear regression. Okay, so I think you might rightfully think that this is a trivial analysis. But it turns out you can do some of the same exact things for kernel ridge regression. So let me describe how that works. So kernel ridge regression can be formulated in exactly the same way as linear regression. instead of having features x, you have essentially random features, capital F, which are some nonlinear function f applied pointwise to a random matrix W times the data. This gives you a set of random features that you could also consider as the post-activation units in the first hidden layer of a neural net at initialization. So capital F is this matrix of post-activation units. And okay, just writing the regression problem in terms of F, you get exactly the same phenomena as in linear regression, but you just replace X transpose X with F transpose F. This is the same kernel trick that I'm sure all of you are aware of from the kernel method literature. In this context, I just want to highlight that everything goes through the same way as I just described. We get an exact analytic expression for the time-dependent training loss. But now we need to know how to evaluate this resolvent and the trace of it to get the Cauchy transform of now F transpose F, which is some complicated, non-trivial random matrix and not just a product of Gaussian random matrices. So how do we compute the Cauchy transform of F? So let me describe a couple methods that can be used to do this. The first method is what you might naively try to do, which is basically just to expand this matrix inverse for large values of z. And you get what's known as a moments expansion. The right-hand side here, the trace objects are the moments of F transpose F. And if you just follow your nose and write out the explicit expression for the k powers of F transpose F, then you get this string of Fs. And the indices here are just instantiating the trace and the matrix multiplications. And it turns out through a complicated combinatorial analysis evaluating some high-dimensional integrals that you can, in fact, evaluate this expectation to leading order in 1 over the width, and then resum the series and get an expression for this Cauchy transform. But this is actually a very bad way to do things. It's the first way we did it a couple years ago and got a result. But we've since realized there's a much better option, which is in many ways quite a bit more interesting as well, which is utilizing a concept from random matrix theory that probably many of you are familiar with, known as universality, which in essence suggests that most of the properties of a random matrix that you might consider, like its for example, spectral density, don't really depend in detail on the distribution of the individual elements of that random matrix, but instead depend only on some low-order moments of that distribution. And here we're sort of building on that concept, and it turns out that you can replace F by any matrix which has the same low-order moments, so moments through order 2. And if you do that, then for the quantities that are under consideration here, you get exactly the same results. So in fact, it turns out that there's a matrix we call F-lin that has the exact same low-order moments as F. So this is just something you can check by explicit calculation in this asymptotic regime. And notable properties of this F-lin matrix is that it's linear in the argument to F, namely it's linear in W times X. The constants here depend on the nonlinear function. They're like Gaussian expectations of F squared and F prime. And there's additionally the addition of some independent random matrix A. But it turns out that F-lin has the same second moments, and using essentially this concept of universality, one can replace F with F-lin anywhere it shows up. So what does this buy us? It doesn't buy us much unless we have some additional tools at our disposal. And those tools come from random matrix theory, in particular from the theory of free probability, which basically, in this context, gives us a way for adding and multiplying certain kinds of non-commutative random variables, namely matrices that are what's known as freely independent. And so the upshot here is if we can establish that these matrices A, W, and X are free, then we can compute the Cauchy transform of F, which is what we're after, in a simple way by manipulating the Cauchy transforms of those constituent guys, which we'll know a priori. So this is the basic idea, and before I really go into more details here, let me just take a brief detour to say a little bit about what is this free independence. So as a way of characterizing free independence, I would first like to remind you of independence in the classical sense from one particular point of view. So the point of view I'd like to emphasize is that of the cumulants. So I'm sure you all know cumulants, or have heard of them to some extent, but to remind you and to define them, the generating function of cumulants, k, is just the log of the moment generating function. So the cumulants themselves are defined by this exponential generating function k. And if you just take this definition and follow through some combinatorial identities, then you have an explicit definition for the cumulants kappa. And they are basically turn out to be sums over partitions of the variables x1 through xn, or you could think of partitions of n. So the mixed moments on the left-hand side of this equation of x1 through xn are a sum over partitions of cumulants evaluated at blocks of those partitions multiplied together. So there's a bit of a mouthful. I think it's a little easier to just look at some examples of cumulants. So at n equals 1, the first order cumulant is just the mean. At n equals 2, the second order cumulant, kappa x1, x2, one can compute by the expectation of x1, x2, and kappa at lower orders, which you might assume to know by an inductive or recursive approach. Likewise, the partitions at n equals 3 are 5 in number, right? So if you take the set 1, 2, 3 and ask how many ways can you partition it, you can either have all three things being in the same block. You have x1, x2 in one block, x3 in the other, etc. And likewise for n equals 4. And if you just do this, it defines an inductive procedure for defining the cumulants. And this is one way of understanding independence in the classical sense. Independence implies that the mixed cumulants all vanish. So this is one definition of classical independence. So it's this definition that generalizes nicely to free independence. So you do exactly the same thing, but you define free cumulants, kappa, instead of in terms of a sum over all partitions, you sum over what's known as non-crossing partitions. So it's just a slightly different sum, and it gives you a slightly different kind of cumulant. And what is the difference between these two sums? The difference first shows up at n equals 4. So to give you a sense of what this looks like, here's a visual representation of partitions of the numbers 1 through 4. There's 15 of them. And the integers are grouped by these shapes. So for example, the bottom left, you have 1 in one block and 2, 3, 4 in another block. And I think it's obvious by inspection here which is the crossing partition. So in the classical sense, you would sum over all of these partitions. But in terms of defining the free cumulants, you'll only sum over these non-crossing partitions. And this distinguishes the two cases. And so, for example, n equals 4, there's one crossing partition which you eliminate. And this gives you some different definition for the fourth order free cumulant. And it differs from the fourth order regular cumulant. The statement of free independence can be cast as just a statement that the mixed free cumulants vanish. Okay, so this is maybe more about cumulants that you wanted to hear. But the basic point here is that if you are able to establish that your random matrices obey this free independence property, then you can do some really cool stuff. So for example, if you have two free random matrices A and B, then you can add and multiply them in the spectral sense. So you can get the spectrum of A plus B and the spectrum of A times B simply by knowing the spectrum of them independently. So the way this works is through an object called the R transform for addition, which is defined in terms of the Cauchy transform that I introduced previously through this functional equation. So how does this work? So you take the spectrum of the individual guys, you compute the Cauchy transform, you solve this functional equation to get the R transform, then the R transforms add, and then you can project back to get the Cauchy transform of the sum and the spectrum. Likewise, for the S transform, there's a way to multiply random matrices that are free. And okay, so coming back to kernel ridge regression, the point here is that W, X, and A are all free. So we can use this R and S transform to compute the Cauchy transform. And the input to this procedure only requires knowing the Cauchy transform of the individual matrices. And if we know those a priori, by virtue of knowing their spectra, for example, then you're done. So to remind you, we have this somewhat now complicated procedure, but straightforward, I mean, it's just purely algebraic way of computing this Cauchy transform. And it gives us an analytic expression for the training error as a function of time in kernel ridge regression with these noisy labels. And I'd like to emphasize here that the result doesn't depend on the input being Gaussian. So in fact, any distribution for which you know the spectrum of the data covariance, one can apply this procedure to. Oh, okay, so here's just a proof in principle here. This is now the training error as a function of time for kernel ridge regression when the targets are IID Gaussian random variables. And the left panel has a number of hidden units N1, number of random features, which is smaller than the number of features itself. So as you'd expect, you see relatively poor performance, even on the training error. In the middle, you have the same number of hidden units as input features, and on the right, you have more. And you can see that you get lower training loss. No, so I'm going to come back to the test error. And the answer is no, precisely because you're in this high dimensional regime. So if you were to take the limit that phi went to 0, then it would be closer to the classical regime, and you could ask what happens in that case. The answer may still be no, I'm not entirely sure. So great. Okay, so so far you may have thought this was a kind of useless exercise in the sense that we've only been able to compute quantities that are training error, and that we've looked at these IID Gaussian labels. But this was just to introduce some of these tools. And now I'd like to discuss how we can, in fact, describe generalization error in these high-dimensional kernel ridge regression systems. So for concreteness, I'd like to take a joint XY distribution, for which Y is generated by a teacher model. So consider the case where Y is just the output of some single hidden layer neural network for some fixed random weights V1 and V2. And I'm going to actually take the width of this teacher network to go to infinity in the same limit that I am for the rest of the quantities in the system. And in the same way that I argued strong universality allows us to replace F by some version F-lin, in high dimensions, we can also replace Y by such a linearized version. So here there's some new constants in the two terms, and v1 and v2 show up, but essentially this is this sort of similar decomposition that we had for f. Okay, so coming back to just the expression for kernel ridge regression, we have this simple setup. We know the optimal weights. And what we want to do is compute the generalization error. So what that means is take an unseen test point, x tilde, and we pass it through to get some random features, f tilde, and we know the targets are y tilde by passing it through the teacher. So to compute the test error, we need to compute this expectation over x tilde of the predictive function, which is determined by w star, evaluated at this test point, minus the target y tilde. So we do exactly the same thing that I mentioned previously. You expand this into 3 trace objects. But unlike before, evaluating these objects is non-trivial because the y's, f's, f tildes, q's are all correlated. So what's the trick? How do we actually proceed here? Well, we utilize, again, this strong universality to apply these linearizations to all of the relevant terms inside these trace objects. So just to unpack this for a second, you have an expression for the test error. It looks nasty. You apply this linearization, and actually it looks much nastier then, because you have an explosion of terms, because you expand out all of these sums of 2 terms in many places inside these things. But the point is, anytime you see a v1, v2, b tilde, or a tilde, then you can evaluate sort of expectations over those trivially, because the only complicated part of these expressions is q, which is the inverse of f transpose f. And without this inverse, everything is just a low-order polynomial in these matrices, and you can evaluate these trace objects trivially. But q depends only on w, x, and a, not on the other guys. So if you just push through these tedious calculation, what you find is that the test error can be decomposed into a sum of terms, which either contain 2 factors of the resolvent q or 1 factor, and it could be sandwiched with some low-order polynomials in w, x, and a. So the question now is, to evaluate the test error in this student-teacher kernel ridge regression setup for a non-trivial, it's a non-trivial input-output distribution. The problem boils down to evaluating the trace of rational functions of random matrices. So it turns out that you can do this, and the way you do it is with yet another kind of linearization and using a kind of souped-up version of free probability. Okay, so this new kind of linearization is actually a somewhat old result from different areas, including control theory community, which basically says if you have some rational function of non-commutative variables, then you can represent that in terms of basically evaluating the inverse of some matrix that's linear in those non-commutative random variables. So R is some complicated rational function. The variables don't commute, but you can write it in this simple form. You transpose M inverse V, where M is linear in the non-commutative variables xi. So I mean, the proof here is constructive and very simple. You just kind of iteratively apply some sure complement identities, and you can construct such a representation algorithmically. So here's an example of how that looks. So consider again this resolvent matrix Q in its linearized arguments f lin, which, throwing away some constants, is wx plus a transpose times wx plus a minus the inverse. And it turns out that this matrix can be written in the U transpose M inverse V form by just moving to this block structured object. So this is just an identity you can check. And the crucial point here is that n is linear in W, X, and A. So naively, you would think if you were a practitioner of free probability, based on what I said earlier, that we were in great shape. Because we now have a sum of random matrices. They're block random matrices, but we have a sum of random matrices. The matrices are all independent random variables. And so one would hope one could just use the R transform to basically compute the trace of Q. However, it turns out that these additive terms are actually not free because of the block structure. So what do you do about that? Well, what you can do is instead regard this block structured matrix M as a linear function in W, X, and A, but with coefficients in 4x4 matrices. And it turns out that this concept of free independence can be salvaged, but what you have to do to salvage it is to account for the non-commutativity in the space of these 4x4 matrices. So how does that work? That brings us to the topic of operator-valued free probability. So I'm not going to say many details here, as I know I've thrown so many at you already. But the basic idea here is to just persist the calculation as far as possible in this operator-valued space before projecting down to the scalar-valued objects that you ultimately care about. So there's a generalization of the Cauchy transform, which instead of computing the trace of the resolvent, where here you would regard M as this big block structured matrix, and you just want to compute its inverse in its trace. In the operator-valued context, what you would instead do is regard M as a block structured matrix. You perform this inverse, but then you only trace along the blocks, and you persist the block structure after computing the trace. So this is in our example before would be a 4x4 matrix would be the output of G. So it turns out that there is an operator-valued R transform that obeys the same equation as the regular R transform that allows us to obtain from the operator-valued Cauchy transform an object which is additive in terms of in the space of operator-valued R transforms of A and B, they're additive. So actually, this more or less is all the pieces we need. So if we're able to add operator-valued free random variables, then we can use this representation for M, essentially. I mean, there are many complicated terms like this that one needs to compute, and use this whole business of moving to the space of R transforms, do the addition, project back to operator-valued Cauchy transform, and obtain the result for the trace of the resolvent. So the only missing piece here is what this concept of operator-valued freeness is and how it relates to freeness in the standard case. And the only thing really you have to keep track of is the fact that the cumulants become operator-valued as well. So whereas in the standard case, the cumulants are all commutative, in this operator-valued case, you have to keep track of that. And that means you keep track of the nesting structure of the partition. So instead of pulling kappa outside, you have to sort of leave it inside and keep the relative ordering of the x's intact. But once you do this, you get some kind of operator value definition of the kappas, and then you can establish that all of the terms that show up in these linear pencil representations for these trace objects are in fact free in the operator valued sense. So then you can add them and obtain the ultimate goal, which was the expression for the test error. So the details, as you can tell, are quite complicated, but the results are really nice. So here we have basically the result of this quite convoluted procedure that gives us an analytic expression for the training and test error for kernel ridge regression in this student-teacher setup in the high-dimensional regime. So in solid lines is the test error, and dashed lines is the training error. So I have a couple setups here, both of which are in the scenario where the number of input features is equal to the number of hidden units is equal to the data set size. So this is precisely in the regime where you might expect strong overfitting to happen when the regularization constant gamma is small. So the different colors going from blue to red are increasing amounts of regularization. So on the left, you see as the time, a gradient descent time evolves, the weakly regularized models begin to overfit. And you see precisely the behavior that you would expect, which is that for some early stopping time, the generalization performance is best. One thing to note here is that as the regularization constant increases, it seems that early stopping no longer buys you much. And furthermore, that the best generalizing model here is very close to the t equals infinity performance of the best ridge regularized model. So one observation, although we haven't yet done a detailed study here, is that it may not be the case that early stopping buys you much relative to explicit L2 regularization. I wouldn't put a lot of confidence in that statement, though. The point I really would like to make is that this formalism gives you the tools to do the analysis to figure out the answer, at least in these setups. So you can do other things. So here are, again, test error in solid lines, training error in dashed lines. The x-axis now varies the dimensionality of the hidden units. So you could interpret this as when n1 over m is less than 1, you're in the underparameterized regime. When it's greater than 1, you're in the overparameterized regime. In the top row, we have the number of features equals the data set size. And in the bottom row, it's half the data set size. And the left column is when the teacher model is linear, and the right column is when it uses a nonlinear function hyperbolic tangent. So you see this, I think now, characteristic double descent behavior, whereas you increase the number of parameters, the test loss either stays constant in the top or goes down in the bottom until you reach this critical parameterization threshold when it blows up, at least when you have low or no regularization. But then slightly past that threshold, the test error drops again, and as you increase the number of parameters, you generalize well. And in fact, this is maybe most clearly evident in the top left panel. If you push out to very high overparameterization, the far right, and use very low or no regularization, then you actually get the optimal generalization performance. I'm not claiming that happens in general. I'm only claiming that here's a formalism that allows you to compute it. So it's very weakly regularized.
And red is very
Yes.
Mm-hmm. But in the very overparameterized regime where the ratio is like 100, you're saying that if I train for infinitely long, it doesn't matter how much regularization I do?
Yeah. So you can see there's a small effect as you change the value of gamma, going from red to blue at the very far right of the top left curve. But as it becomes deeper and deeper blue, you get slightly lower MSE. So it changes the result. It's just, it seems like the asymptotic limit here that gives you the best performance is the one in which the overparameterization ratio goes to infinity and the regularization constant goes to 0. i.e., if you're only somewhat over-parameterized, you should use L2 regularizer. But if you're infinitely over-parameterized, then you shouldn't.
I think I just can't see where the blue line ends up over there. Are they just all the same?
They are very closely overlapping, yeah. It's slightly less. Okay. So I'd like to deliver now your final course of linearization. You heard about this already earlier today, so hopefully this is no longer a surprise. But I'd briefly like to consider training all of the parameters in a single hidden layer neural net. So we'll call that output of that network n. Depends on some parameters theta, which are collectively W1 and W2. And the observation, now made in many different ways, is that in many cases, as the width gets large, the parameters themselves individually move less and less away from their initial values. So this obviously motivates a linear approximation of the input-output map, where you expand theta about its initial values. And it turns out, as the width goes to infinity, you can truncate this expansion at first order, and it gives you the exact dynamics. So J0 here is the Jacobian of the model, Jacobian of the output of the model with respect to its parameters. So this is just a linear differential equation, which you could solve exactly. And the dynamics are given by the so-called neural tangent kernel. The neural tangent kernel theta is just J transpose J. And it decomposes into a sum of per layer kernels, where theta 1 are products of Jacobians of the weights with respect to the first layer, and theta 2 with respect to the second. And there's a particular form in the single layer case how these two kernels decompose in terms of the constituent matrices in the problem, which are X, the data, F, the nonlinear features, and F prime, the kind of derivative features you can think of. And there's a diagonal matrix that has W2. So as a quick aside, the output of the neural net at init, N0, actually just ends up contributing some unnecessary variance to the MSE. And you can effectively set it to 0 by the following trick. So you could define a variance-reduced network, which is defined as just the difference between two copies of the same network with independent parameters, except that the parameters theta 1 and theta 2 are initialized to the same values. So it turns out that this completely eliminates it sets to 0 the output of the function at init, but the neural tangent kernel theta is the same. So the dynamics are equivalent, but you get rid of this unnecessary variance term. So now let me just briefly talk about the two-layer kernels. So theta 2, the kernel derived from differentiating with respect to the second layer weights, is exactly this random feature kernel that I was discussing in the rest of the talk. It's just K. And as I mentioned and have been discussing, the non-trivial behavior comes in the asymptotic regime where all of these scales are going to infinity at the same rate. So the number of features, the number of hidden units, and the data set size go to infinity at the same rate. The first layer kernel, however, is actually quite a bit more complicated. So it has this element-wise or Hadamard product structure. And in fact, owing to this structure, there are at least two non-trivial scaling limits. So the first scaling limit is when the network is linearly over-parameterized. So the number of parameters is roughly n0, n1. And if that's on the same order as the number of samples m, then it turns out that the fluctuations in this first term of the Hadamard product, f prime transpose f prime, that it's not just the mean of that term, but the fluctuations in that term are important and contribute non-trivially to the spectrum of theta 1. And to make matters worse, it turns out that you can end up with a large number of large eigenvalues. And so this thing is actually quite nasty in this limit. And we don't have, at the moment, the best way of analyzing it. So instead, the analysis I'm going to talk about is in the quadratically overparameterized regime. So this is the same scaling that we've been using before, but in terms of theta 1, in terms of the neural tangent kernel, it means that the number of parameters is quadratic in the data set size. And in this case, it turns out really you don't need to worry about fluctuations in this term, only you need to worry about the mean, and that theta 1 then has a really simple form. So combining that with the form for theta 2 that we already know, using all of the tools from operator valued free probability that I laid out, you can compute the NTK kernel regression error. So, so before describing this plot, let me just say one word about what I mean by the NTK kernel regression. What I mean is that you take the kernel that is defined by the Jacobian of the model, just the NTK, and perform kernel ridge regression with that. So if the data set size is finite, this will give you the equivalent system to gradient dynamics. If the data set is large, like we're considering here, then it's no longer necessarily the case that the gradient dynamics are governed by the NTK dynamics, because the condition that the parameters don't move far from their initial values can be violated. Yes. Yes. Although I think this is still an active area of research to know exactly what the conditions are, but empirically the answer is yes, they move. So we're looking at kernel ridge regression with the NTK kernel, and here I've basically just reproduced the result I showed you previously from the case where we're talking about this random feature matrix K, which is equivalent, it turns out, to the second layer NTK kernel in the variance reduced setting. So now you can overlay what happens when you look at the full NTK. So actually what this shows is that as you increase the number of parameters for this neural tangent kernel, the generalization performance gets worse. But you might ask, okay, well, is this because you have this annoying extra variance term coming from N0? So what happens if you get rid of that? Well, it helps the behavior for large N1, but now you have this hump. So this is quite interesting, but you might be thinking, does it really make sense to overlay these curves against N1, which for K, the blue curve, corresponds to the total number of parameters. But for the green and orange curves, it's the width, it's the square root of the number of parameters. So instead, if you wanted to really know the behavior of these systems as a function of the number of parameters, what you would want to do is sort of pull these apart and change the x-axis to the number of parameters. And sort of the qualitative picture that I think emerges from this analysis is that you have this sort of standard double descent behavior on the left side, but there's some new phenomenology that's happening in this other asymptotic regime. In particular, it seems like you can generate a peak, a second peak, when the number of parameters becomes quadratic in the number of samples. So I should mention that this is not a rigorous kind of derivation of the full plot in the space of number of parameters, because the left side is really a different model than the right side, in the sense it's the NTK with respect to the top layer weights. So it's not like we're really varying a single parameter to move left to right. This is basically joining two different asymptotic regimes that we computed separately. But still, it gives this striking behavior, and leads me to maybe speculate that we should consider that there may be more complicated behavior as a function of the number of parameters. So here's a sketch of what that might look like. The classical regime where the data set is large, i.e. the number of parameters is much smaller than m, you get the canonical picture where the test error starts going up. But then you enter what we call RMT phase 1, random matrix asymptotic regime, where the number of parameters is roughly on the order of the number of samples. And you get the spike that we're somewhat familiar with now. Then there's a regime we don't really know how to analyze that lives in between until you get to the regime where you're quadratically overparameterized. And then a second set of asymptotics kicks in. And it seems like you can, at least in these cases we've looked at, generate a second spike in generalization error. And then you can go down again as you move into the heavily overparameterized or exact NTK regime. So actually, that's all I have to say today. I'll just leave you to look at this plot. And thank you so much.
We have time for a few questions before the poster session.
Very nice analysis. So what happens if you start not from Gaussian?
So it's a good question. I think from this sort of in the standard NTK picture, when the data set size is finite, then, roughly speaking, you get central limiting behavior. It doesn't matter too much as long as the distribution is not pathological. But actually, in the case that we're considering here, the distribution on W actually does matter. We haven't done the calculation, but you could. In essence, what you would do is, in these free probability calculations, you would replace this input Cauchy transform of W, which we use as essentially a Marchenko-Pasteur version for Gaussian W, and replace it with the one that's induced by the distribution you did use. And it would change some of the details. I don't know how much, if at all, it would change the qualitative picture here.
Well, I don't mean necessarily that individual weight distribution is something else from Gaussian, but the correlations. Strongly, yeah. I mean, the brain, when it learns, and mature brain, when it learns something new, probably doesn't start from Gaussian.
So as long as the correlations aren't too strong, what I just said is true. If the correlations are strong, then everything breaks down.
Hi, very interesting, especially the triple descent. So I guess that's with 2 layers.
Yeah.
And so I guess any conjectures about with D layers, is it 2 to the D, ups and downs, or?
I believe with D layers, then you'll still have these same 2 asymptotic regimes, but the second asymptotic regime might generate some more fine-grained structure. But this is actually sort of outside the scope of what we know how to do currently, unfortunately.
And why is that? Why is it out?
So one of the
What's
details
the technical
I glossed over slightly was that we actually need the output of the network to be one-dimensional. And that's essentially because of this D diagonal matrix with a vector of the readout weights that happens, that's sandwiched in between the F primes here. In the multi-layer case, instead of having a nice matrix representation for the kernel, you get a kind of ugly tensorial object, which results by the fact that you have this extra dimension. And so far, we haven't cracked how to solve that case from the RMT side.
Thanks, very interesting.
Mean that if the input is Gaussian, then the input to the second layer is also Gaussian in this limit? Like, is that an equivalent statement too?
I don't think so. So I think these statements are really only about the kernel, and you get these kind of universality conditions on ways you can represent the entries that have the same spectral information. If you just looked at the output of the first layer, yeah, this is not going to be Gaussian, even in this limit. So in terms of the function that you compute, you don't get to use this same kind of simplification. It's really only in this sort of computing these certain kinds of statistics.
All right, then let's thank our speaker one more time.